Hello students, welcome back. We just went through some example problems on the distribution of primes. They were the simplest and the easiest types of problems. And here they are. First, we went through Euclid's theorem on the infinitude of primes. There are infinite many primes. In other words, prime numbers are distributed all over the set of positive integers C+. Consequently, there are infinitely many. As for the proof, here's the key idea. We use the proof by contradiction and assume there are only finitely many. And then the key point. Define capital Q as the product plus 1. That allows us to do this modular arithmetic. The product is congruent to 0 modulo any pi, so we have 0 plus 1, we have remainder 1. So no pi divides Q. That was a key idea, and therefore capital Q has no prime factorization, and there goes a contradiction. How about the second problem? The first problem was about the distribution of primes all over Z+. This time, let's take a partition of Z+. Divide set of positive numbers into 4 pieces, basically, or partition. If I divide a positive integer by 4, the remainder can be either 0, 1, 2, or 3. Remainder is 0, then it's a composite number, so no prime number is there. It's a multiple of 4. Now remainder is 2, then it's an even number, so there's no prime except 1. The smallest positive number, smallest prime number, 2. That's the only even prime. So all the primes are of the form 4n plus 1 and 4n plus 3. And as for the primes of the form 4n plus 1, yeah, there are infinitely many, but we are not ready to prove it. This example problem is about there are infinitely many primes of the form 4n plus 3, those with remainder 3. And the key idea was kind of similar to this. Define capital Q as 4 times the product plus 3, and then we use similar kind of modular arithmetic. Look at it modulo pi, because this is congruent to 0 modulo any pi. And also look at it in terms of modulo 4. This is 0 modulo 4. So that's another problem regarding the distribution of primes, but this time modulo 4. And both are about infinitely many primes, by the way. Now let's go to the next step. This time let's consider the upper bounds, some of the upper bounds of the primes. So the nth prime is less than or equal to, wait a minute, haven't you seen this before? Yeah, it appeared right here, except that P1 through Pn minus 1 are a little bit different this time. This time we're going to define Pn as a sequence of primes in the increasing order. So those are the prime numbers 2, 3, 5, 7, 11, 13, 17, 19, and so on in the increasing order. And this theorem is saying, this inequality is saying, the nth prime is bounded by this product of all the primes thus far plus 1. So the nth prime cannot be outrageously far away from the other n minus 1. And we can improve this a little bit further if I start from n is 3. So here we have plus 1. Here we have minus 1. So the second inequality is a little bit more improved. So the nth prime cannot be outrageously far away from the first n minus 1 primes. It's less than the product of all those primes thus far minus 1, when n is greater than or equal to 3. Well, let's check actually. Starting from second prime, that's less than or equal to first prime. Yeah, that's it. I'm starting from n equal to 2. In this case, only 1 prime, so product of just 1. And is that true? Well, the second prime is, as a matter of fact, 3, and the first prime is 2. So that's what you're getting. Is this right? Yeah, that's right. We have equality, so the semi-equality works. Now, what if I do this for the second problem? Does it work? So this is minus 1. So is 3 greater than less than or equal to 2 minus 1? That's not true. So this one actually fails. That's not true. Now, if you go to the next step, it'll work out. So third prime, which is 5, and then we have to have product. So 2 times 3 minus 1, that's 6, minus 1, 5. So we have equality here. So it works. This one doesn't. This one does. So we have to start from n equal to 3. So that's a subtle difference between the first and the second problem. And that's generated by this plus 1 and minus 1. Otherwise, the second inequality is a little bit stronger. And the trade-off is, of course, you have to start from the third prime, not the second prime. In any case, those problems are related to the distribution of primes in a sense that the nth prime cannot be too far away from the previous n-1 primes. Now, how do you prove it? Well, this idea will be helpful. After all, the right-hand side is the same, right? Here's a hint. Define Q like this, and no pi divides Q, and that's due to the modular arithmetic. Remember that. The product is congruent to 0 modulo pi, so the remainder is 1, not 0. Therefore, the prime factorization of Q does not involve any of those primes p1 through pn minus 1. And the prime factorization exists, and it must be unique, right? The fundamental theorem of arithmetic. So there has to be a prime factor, say pk, which does not belong to all these. Consequently, we get this conclusion. pk divides q, and then pk does not belong here, so k is greater than or equal to n. Therefore, the next smallest prime, pn, is less than or equal to pk, which less is equal to q. So this algebraic manipulation is okay, but the background, the fundamental theorem, the factorization of q, that being unique as well, all those kind of things has to be filled in. So this is not a full proof, it's just a hint, and I want you to complete it. Now, can you use the same idea to prove part B? This problem. Well, stop the playback and try. Do you get the same thing? Yeah, pretty much the same thing. We can use Euclid's theorem or the same argument as in the Euclid's theorem. It's a bit different this time. We have minus 1, so plus 1, but same idea. Not exactly the same, but same idea. And then modular arithmetic. This product is 0, so this is congruent to minus 1, equivalent to pi minus 1. In any case, pi does not divide q, and therefore we can use the same argument for the same conclusion. Again, the detail is left to the students. Okay, how about the next problem? N is greater than or equal to 1. In other words, for all the primes, the nth prime is less than or equal to 2 to the 2 to the n minus 1 power. Oh my. Can you read this? Oh, maybe it's better with bigger font. Can you read this? Okay, let's prove that. And this time we have a full proof here because this is harder. We used a strong induction. First, the base cases, n equals 1 and n equals 2. By brute force computation, you can check. N is 1, then 2 to the 2 to the 1 minus 1 power. So that's 2 to the 2 to the 0 power. So 2 to the first power, yeah, okay, alright, that works out okay. And then n is 2, then we have 2 to the 2 to the 2 minus 1 power, first power. So 2 to the second power, that's 4. And that's greater than or equal to 3. So it's okay. So the conclusion works for the base cases, n is 1 and n is 2. By the way, why do we have two base cases? Not just n equals 1. Well, that's because we're going to need a second case because we will use the first inequality here. And that works from n equals to 2, you see? So we need the second one. It works for the first one as well, so yeah, we can start from 1. We can start from 1 here, yes. But in order to use the inductive hypothesis and start everything using this, you need the other base case as well. All right, now let's use strong induction. It's not standard induction, it's a strong induction, so it's tricky. Suppose that the conclusion is true for all positive integers less than n, greater than or equal to 2 and less than n actually. So suppose that it works, then you can use this to make this overestimation of this Pn. And then inductive hypothesis says this P1 is less than or equal to this for n equals to 1. This P2 is less than or equal to this by the inductive hypothesis when n equals to 2, and all the way up to Pn minus 1. Like this. And then even the middle part as well. So all these come from the inductive hypothesis, and we have to apply this to all those, so we want strong induction, not just standard induction. Okay, alright, we have up to here. Same base, so we can add up the power. That's the third line, and what do we have? We have a geometric series. I hope everybody remembers the geometric series formula. The common ratio is 2, and starting from 1. So the next term, 2 to the n minus first power minus 1, divided by 2 minus 1, but we don't need that. 2 minus 1 is 1. So that's the computation of this geometric series. Next, we make another rough overestimation. Instead of this 1, replace with something much bigger. 2 to the 2 to the n minus first power minus 1, same as this. Much bigger. So we have this inequality, and then this and that are the same, so twice of the quantity. That means this is 2 to the first power times that, so we are just adding up the power. So minus 1 and positive 1 cancel each other out. In the end, we get precisely what we wanted. 2 to the 2 to the n minus first power. So that completes the proof. By the way, as a result, there are at least n plus 1 primes less than 2 to the 2 to the n power. Apply this one to each of those. We have n plus 1 primes are less than all these. We may use it later, maybe not. It depends. Okay, so much for another example on the distribution of primes.